Based on some sketching, we think we've discovered a reflection property for the parabola. The reflection property we think we see is that a ray coming in perpendicular to the directrix and reflecting off of the parabola is reflected directly towards the focus. So that means in this diagram here, the focus is, this is the focus here, this is the directrix. If we had a ray coming in like this, it would bounce directly towards the focus. So it seemed pretty convincing when we did our sketching, but let's see if we can actually prove why that should be the case. So let's see. Let's call this point here P, I guess, for lack of a better name. Because P is on the parabola, that means that the distance from F to P has to be equal to, let's call this point down here A. Because the point P is on the parabola, that means the distance from F to P has to be equal to the distance from P to A. Because that's what it means to be on the parabola. Also, this incoming ray is an extension of the line from P to A, right? Because the ray that's incoming is coming in perpendicular to the directrix, and the line from P to A is perpendicular to the directrix, because that's how you measure the distance from the point P to the directrix. You have to measure it in a perpendicular distance. So what we're going to do is take this, take the angle from F to P to A and bisect it to get a line that we're going to call L, and that line is going to look something like this. Okay, so the key fact for this line is that L is tangent to the parabola. Now, we're going to have to prove this, of course, but first let's see why this proves the reflection property. So if this is actually true, then, actually, sorry, before I say that, let me just note that since we've bisected this angle from F to P to A, that means that these two red angles are equal to each other, because we cut the big angle in half, and that means the two small red angles or so are equal to each other. Okay. Now, if this line L is actually tangent to the parabola, then the angle that I'm going to call M, which is this angle right here, is equal to the angle N, which I'm going to say is right down here. Okay, and that's because if L is tangent to the parabola at P, then M and N are vertical angles, right? Angles across an intersection of two lines are always equal to each other. So if L really is tangent at P, then these two angles are equal to each other. But we already know, because of how we bisected the angle, that the angle N is equal to this outgoing angle, which I guess I need to give a name. Let's call that angle O, I guess. Okay, but M is the incoming angle for the reflection, and O is the outgoing angle. Right, so I guess that's really why we need to know that L is tangent. For M to be the incoming angle, we have to measure the angle from the incoming ray to the tangent line. And then same thing for O to be the outgoing angle. It has to be the angle between the line segment from F to P and the tangent line. So if we know that L is tangent, then M is equal to O, and M is actually the tangent, the incoming angle, and O is the outgoing angle. Okay, so let's prove that L really is tangent to the parabola. So to prove that L is tangent to the parabola, we're going to show that no other point on the parabola, no other point on L is on the parabola. If we can show that, we're done, because that means all of the parabola is on one side of this line, and that means that L is a tangent line. So let's take any other point on this line. So take any other point I on the line L, say up here. Okay, what we're going to do is connect F to I. We're going to connect F to A, and we're going to go straight down from I to the directrix to make a point B. Okay. Also, we're going to connect F and A like this. Okay. F and A, when we connect them, gives us one more point, which I guess we'll call C right here. Now, notice that there are three things we know are equal. We know P, the distance from F to P, is equal to the distance from F to A. That's something we noticed before up here. We know that the angle FPC is equal to the angle APC. Right? That's the two red angles. We already noticed that those were equal to each other. And then finally, the line segment PC is the same length as the line segment PC because that is the same line segment. Okay, but notice that this is a side, another side, and an angle for two different triangles, right? There's the triangle FPC and the triangle APC, and we know that they have two congruent sides, and the angle between those two sides is the same. But we know that in this situation, if you have two triangles with two sides that are the same and the angle between them the same, that means that these are the same triangle. So these two triangles are actually the same triangle. If you look at the diagram, that's kind of plausible. It looks like they're mirror images of each other, and we've just proved that, in fact, they are actually mirror images of each other. Okay, so since these triangles are mirror images of each other, that means that all of their corresponding parts are equal. In particular, the line segment from C to F has to be equal to the line segment from C to A. So this red line segment is equal to this red line segment. Notice also that the angle ICF is equal to the angle ICA because they're both right angles, like we noticed just a second ago. I guess it doesn't matter that they're right angles. What matters is that they're equal to each other. And then finally, notice that line segment from I to C is equal to the line segment from I to C, again, because they're the same line segment. So these three facts together, again, give us a side angle side proof that the triangle ICF is the same as the triangle ICA. Okay, that's these two, this big red triangle here and this blue triangle here. Okay, and in particular, that means that the line segment from I to F is equal to the line segment from I to A. Okay, so this top red side is the same as this right blue side. Okay, but so we're almost there because, right, to know if the point I is on the parabola, we need to compare the distance from I to F and the distance from I to B. Well, so we know something about the distance from I to F, so let's compare that to the distance from I to B. Well, we know that the distance from I to F is equal to the distance from I to A. But look, we have this right triangle right here, and I to A is the hypotenuse of that right triangle. But the hypotenuse of a right triangle is always longer than either of the legs. So the length from I to A is definitely larger than the length from I to B, because from I to B is a leg of this right triangle, and I to A is a hypotenuse in this right triangle. But this means that the distance from I to F, so the distance from I to the focus, is greater than the distance from I to B. Not equal. This means that I is not on the parabola. But since I isn't on the parabola, that means that there are no other points on this line L except for P. That means L is tangent, and that means that we're done. Remember, all we needed to show was that the line L is tangent, and we've done that.